Okay, so what I'm going to focus in on today is aviation and the concerns about how aviation affects climate. On Tuesday night I gave the Chancellor's lecture on campus, and there I talked about climate in general. So today I'm not going to really get into that other than this first slide, just to make sure that everyone is clear that the concerns about climate change, and particularly the impacts of human activities in affecting our climate system, is one of the most important issues facing humanity and our planet. And it's something we need to be taking very seriously and figure out the right policies, both to reduce the effects of this issue, mitigation policies, but also we're going to have to adapt to certain changes that will require adaptation policies. Now, the thing to do is we need to avoid the worst of the potential changes, and I won't be going into those today because I am going to stick primarily to aviation. But there is no question about the strength of the evidence that the planet is warming. The evidence is extremely strong that most of this warming can be attributed to human activities. We cannot explain the temperature record of the last 50 years without incorporating human activities as being the primary cause of that. It's very careful analyses that have done this. This graph up here actually is a comparison of a model calculation of the climate system with the observed record. So not only is the temperature changing, but we're seeing many other changes in the climate system, including changes in extreme events, precipitation, large precipitation events, greater than 2 inches of rainfall per day, the kind of day we're having today, have increased by over 30% in the last 50 years in the Midwest, and doubled over the last century. So we've been seeing a very significant increase in such events here. Sea level is rising, and there's a number of other things going on. So climate throughout our planet will continue to change significantly unless we do take the kind of major actions I was talking about before. And there's a number of big concerns about potential impacts that could be extremely important. Now let's focus in on aviation. The concern about climate change impacts is potentially the most serious long-term issue facing the aviation industry. That's not my statement, actually. That's a statement that arose from the International Civil Aviation, ICAO, I think it's, International Civil Aviation Organization, which is the UN body that oversees aviation throughout the world. Aviation does obviously play a key role in the world economy. Aviation supports 8% of the global economic activity and carries 40% of the value of freight. Aviation activity has generally outpaced economic growth. And the U.S., which has 4% of the world's population, has 40% of the aviation activity. If we look at past growth in aviation traffic, we can see that over the last 40 years, we've seen increases, breaking this down to different time periods, ranging from about 5% to 9%. And so a very significant increase in terms of the increase, I think it was per year, in the number of passengers. So there has been significant growth. If we look at the projections for growth, and of course this last year or two we've seen the effects of economic problems throughout the world, which also has had a great impact on aviation. But nonetheless, if we look at the long-term projections, and this graph came from FAA, we can expect by 2025 something under a factor of 2 increase in the number of passengers again. And projections from Boeing are at least that high and somewhat higher in some cases. So this is pretty typical of what you see in terms of types of projections. Now, the concerns to the environment related to aviation are several-fold. There's three primary environmental issues that FAA, for example, or ICAO focus on. One is noise near airports, and that's where most of the money goes these days, by the way, is to try to deal with that. Secondly is air quality near airports, which is not a major issue. There's some concern about particulate emissions near airports, in some airports, but overall not a huge issue. And the third one is climate and the potential impacts, including the potential impacts of aviation emissions on stratospheric ozone, tropospheric and stratospheric ozone. Carbon dioxide emissions is part of that. The main concern about climate is because of increasing amounts of carbon dioxide, as well as some other what are called greenhouse gases, radiatively important gases that absorb in the infrared. And as you'll see in a second, aviation accounts for a little over 2% of the total emissions from human activities worldwide of CO2. Water vapor is another emission that is relevant, particularly if those emissions occur in the stratosphere. In the troposphere, it's too little compared to the amount of water vapor that we already have in the troposphere. And so it doesn't make a big difference there, except for in the formation of contrails, and we'll talk more about that later. Some nitrogen, oxygen, but that really doesn't matter. Nitrogen oxides emissions, the heat of the engines can dissociate nitrogen, creating nitrogen oxides. Those nitrogen oxides can react with ozone, and I'll talk later about the formation and destruction of ozone that can occur as a result of that. And there's also some feedbacks that also can impact on methane, which I already said was one of those important, radiatively important gases. Unburned hydrocarbons and CO emissions are so small that our analyses and others have shown that they're just not very important. Emissions of soot can have a warming effect in the climate, and so we need to be concerned about that. Those emissions are relatively small from aviation. Those engines are extremely efficient, but nonetheless, there is some soot, and it might have some impacts, and I'll talk more about that. And then finally, sulfur. Sulfur's in the fuel itself, in the jet fuel. And the sulfur gets into the atmosphere, it converts to sulfuric acid aerosols, and those aerosols can actually reflect sunlight, leading to actually a cooling effect on temperature. Both of those types of particles can have an impact on cirrus clouds and need to be considered for those effects as well. I keep forgetting I can actually change it from here. Now, how large are aviation emissions compared to other sources of emissions? And first of all, realize that on this scale here of annual emissions, it's on a log scale. And so if we look at road traffic, for example, which is 1,122 teragrams of carbon per year of CO2, aviation is about 178. So it's much, much smaller. It just doesn't look like it on this graph because of the log scale. Now, if we look at the amount of CO2 emitted, that accounts for about 13.8% of, in this case, from road traffic, about 13.8% of the total emissions of carbon dioxide from human activities. Ships account for another 2.7%, and aviation about 2.2%. So relatively small effect from aviation in terms of total emissions, but we'll talk more about why the aviation community is really concerned about this.
Global or just the United States?
I think this is global. Yeah. The nitrogen oxide emissions, similarly, the emissions at the surface from road traffic is much, much larger than the emissions from aviation. Similar thing for sulfur dioxide, great difference there. PM10, that's large particles, usually come from mechanical type things. You just don't have any real such emissions from aviation. And in fuel consumption, there's also a large difference. So it gives you an impression of scale. But nonetheless, aviation at approximately 2% of global emissions of human-related carbon dioxide is considered to be important. And part of that is because as we look at the future and these projections that I was talking about, the amount of CO2 emitted is likely to increase relative to other sources. Particularly as we start to work on policies to control other emissions, CO2 starts, or the emissions from aviation start becoming a bigger piece of the pie. One of the things we've got to recognize is any new aircraft are a long-term investment. And that also impacts upon the ability of the aviation community to be able to move quickly if in terms of trying to do policies. Which is why Boeing is already, for example, putting a major effort into developing aircraft that are much more energy efficient, using carbon-based body in the 787, and to lighten the weight, trying to do everything they can to improve fuel efficiency, because not only does that save the airline companies a lot of money for fuel, but it's also kind of preparing for the development of these next generation aircraft in general that will gradually replace the current fleet. Now, if you look at the policy focus for organizations like ICAO, their focus has been on emissions inventories. So the focus has been on how much emissions of nitrogen oxides, for example, should be allowed, and so they spend a lot of time looking at the amount of fuel burn. These are projections, analysis of 1992 and a projection for 2015 that is entirely focused on emissions. However, the reality is we need to be moving away from this just looking at the direct emissions to what are the impacts and what does that tell us about policy. So there's increasing policy relevance on this graph here as we go from the emissions themselves to the resulting climate impacts, climate change and the response, the impacts of that climate change on society and our planet, and resulting damages in social welfare and cost. So we need to be able to move, I can do it from here, remember. We need to be able to move from this top circle of emissions to the bottom where we're actually talking about impacts and damages. And so the science community is trying to work with FAA and ICAO, et cetera, the international body, towards how do we make this happen. Now, I've already listed all those emissions, but I haven't really told you about why they're important and what time scales they're important on. The direct effect of carbon dioxide is obvious. It's one of the most important greenhouse gases, and so emissions of CO2 have a direct impact on climate because of their radiative forcing. Changes in nitrogen oxide emissions can affect ozone, both in the troposphere and the stratosphere. And as we'll see, emissions in the troposphere and the lower stratosphere actually can increase ozone, amount of ozone, while emissions above that into the upper parts of the middle to upper parts of the stratosphere can actually cause an ozone decrease. The resulting changes in ozone affect the amount of hydroxyl in the troposphere. Hydroxyl is the primary cleansing gas of the atmosphere. We call it the Pac-Man of the atmosphere because it reacts with so many important gases to remove them from so many pollutants and remove them from the system. One of the gases it reacts with is methane, and that's the primary loss mechanism for methane in the atmosphere is reacting with OH. So the amount of OH changes, the amount of methane will be affected, and methane is also an important greenhouse gas. In fact, it's the second most important change in greenhouse gas due to human activities. We also have indirect effects from water vapor and particle emissions as a result of contrail formation. I'll talk about that more later. And corresponding effects on cloudiness, particularly on cirrus clouds in the upper troposphere. The direct effects from aerosols, either emitted directly, such as soot. Soot can absorb solar radiation and actually cause a warming effect, or from things like sulfur dioxide and other precursor gases which turn into particles, and in the case of SO2, can actually reflect sunlight, scatter sunlight, and produce a cooling effect. And then water vapor emissions in the stratosphere can have their own direct climate effect. Water vapor is the single most important greenhouse gas, and so we certainly need to consider that as well. Now, part of the problem here, in terms of determining the impacts, is the timescales. Carbon dioxide has a very long lifetime once it's emitted into the atmosphere. There's a very rapid exchange of carbon dioxide with the biosphere, both on land and in the oceans. The eventual removal, though, of carbon dioxide from that system, the Earth's atmosphere, biosphere, ocean system, is the deposition of carbon to the deep levels of the ocean. That takes a long, long time. So as a result, the first lifetime, the first e-folding time, is about 100 years for carbon dioxide. Second e-folding is actually much, much longer because it does depend on eventual removal to the deep levels of the ocean. The other emission effects are much, much shorter. Ozone can have an effect for a year or two after emission. Methane has a 10 to 12 year lifetime, and so you only get the full effect then of nitrogen oxide emissions occur for a long time period, and which of course in the case of aviation they have. Particles stay in the atmosphere a relatively short period of time, even emitted in the upper troposphere where cruise altitudes for aviation aircraft are. And so less than a year. And contrails tend to only last a few minutes to a few hours, typically. Longer-lived contrails, which can also affect cirrus, can affect for longer time periods. Yes?
Water vapor.
It's water. Contrails are primarily water vapor that into a supersaturated atmosphere, and we'll talk about that. Emissions from aircraft, certain current commercial passenger and other commercial aircraft, primarily occur in the upper troposphere and lower stratosphere. They spend about 20% of depending on the Pacific flights, about 20% of the time in the stratosphere. So that needs to be considered. And so understanding of this upper troposphere, lower stratosphere is extremely important because what happens in that region can certainly have an impact on climate. That is the physical, dynamical barrier to the stratosphere. And so water vapor very small amounts of water vapor get transported in the stratosphere going across this tropopause, which is the minimum, basically the minimum in temperature that occurs in the atmosphere. And so how that barrier changes is important to our climate system. It also plays a very important role in the mixing and transport of the chemical species that we're concerned about in terms of the potential impacts of aviation emissions. In 1999, there was a very special assessment of climate impacts from aviation. I was a lead author on 3 different chapters of that assessment. And as mentioned earlier, I was actually a lead author in the first 2 IPCC assessments that looked at climate in general. But we had a very special assessment on aviation in 1999. And one of the conclusions was that detecting the aviation-specific contributions to global climate change is not possible now and presents a serious challenge for the next century. The reason for making that statement is that not only are these effects relatively small compared to all the other things that are going on in terms of human-related emissions, but the signal from such small amount of emissions would be very difficult to detect in a climate model, which also has in the natural variability of the climate system within the model. So being able to detect a very small effect is extremely difficult in those models. So it's difficult to really break out the aviation signal on climate by itself. So we try to do that in different ways, and we use metrics, and I'll talk a little bit about metrics for climate in a minute. Now, there is a paper that is just in the process of being reviewed from Stanford that a friend of mine at Stanford, Mark Jacobson, where he actually claims to have calculated with the climate model, his own model, the effects of aviation. I have, in thinking about his paper, I've pretty much realized, and I've actually made a proposal to the FAA to get some funding to check this out, but basically I don't think he's proven it at all. I think his method for analyzing was very flawed, and so I don't think that we're actually be able to do that. The traditional metric of climate change has been radiative forcing, in which the relationship between the forcing, which is defined as the net change in irradiance at the tropopause after allowing for stratospheric radiative equilibrium, listed here as RF, can be multiplied by a factor called lambda, which is basically the sensitivity of the climate system to a forcing. If the radiative forcing here was 4 watts per meter squared, corresponding to a doubling of CO2, that factor is such that we would get the range of 2 to 5 degrees Kelvin centigrade that corresponds to our uncertainty in the climate system. So you can derive roughly what lambda is. And from that, you can get the change in surface temperature. This very simple representation of the climate system has been used in many different analyses to, as a very simplified look at climate. In aviation, it's particularly useful because of the fact the signal is so small. If we look at the radiative forcing from all those aviation emissions that I mentioned to you, the radiative forcing in terms of milliwatts per meter squared is in the order of, look at the red lines here. The blue are what was in the IPCC 1999 assessment. And you can see how our understanding has now changed. This is based on a paper by Robert Sossin et al. From a few years ago. He's at DLR in Germany, which is the primary place in Germany, in Europe actually, studying aviation effects. And so Robert did an analysis looking at kind of a best update of the radiative forcings compared to the 1999 assessment. And for CO2, emissions had increased, and therefore the effect has increased, but we're still only talking about 0.02 watts per meter squared. Very tiny forcing, as you'll see, compared to the other human-related forcings that have occurred over the last century plus. The effects of NOx emissions on ozone are roughly another 20 watts per meter squared. The resulting effects on methane is minus 10 watts per meter squared. You get a change in methane such that you get a net cooling effect. Reduce the amount of methane. Water vapor effect hasn't really changed in those years. Direct sulfate effect is roughly the same as well. As I said, that's entirely dependent on sulfur that's in the fuel. Direct soot effect has decreased slightly, primarily due to improved understanding of the radiative effects from the soot and better understanding of the soot emissions themselves. Effects of contrails have greatly decreased, and I'll talk more about that later, primarily as we begin to understand the processes better in terms of the number of contrails around the globe at any given time. And then the dotted lines here, we don't have the bars like we had elsewhere for the effect on cirrus. Could be extremely large effect, but lots of uncertainty, so we're unwilling to put bars on it at this point. And that still remains true right now. And so the total, you can see, ranges from about 2 to 3 times the CO2 effect.
What is cirrus and how, I know the heck cloud formation, is that right? Or is that?
Cirrus are very thin, wispy clouds you see at high altitudes. I'll talk a little bit more about the cirrus clouds in a bit. The question is whether the emissions of water vapor leading to contrails. Often you find contrails. Also, you find cirrus where you're in a supersaturated area, which is not surprising. That's how the ice forms. Cirrus clouds are comprised of ice mostly. But these particle emissions can also affect that.
And the reason it is positive is because it prevents radiative transfer to the outer space.
Yeah. Well, essentially, it helps trap radiation from the infrared and keeps the Earth a little warmer. On the bottom here, I'm sorry?
Can you explain methane? How does that cool?
I'll talk more about methane in a little bit, and ask me again if you don't understand it at that point. The level of some scientific understanding has not really changed much. We understand the CO2 effect pretty well. We have a pretty good understanding for the effects of methane and ozone. It's listed as fair here because there's still some new studies that need to be done, and I'll talk about those. And that's pretty much true until you get to the cirrus, where the understanding is extremely poor and remains extremely poor. This is taking that previous graph, a new estimate that was done in IPCC for IPCC 2007. This is actually taken from a very recent paper. But it's essentially just turning the previous graph on its side and putting some uncertainty bars on each of the items. We can contrast that. So if you looked at that total effect, we're talking about 0.055 in terms of total aviation effect, not including cirrus. If we include cirrus, it can get larger than that, maybe 0.09 or 0.08. Let's contrast that to the radiative forcing on climate since 1750 throughout the planet from all human-related sources. And we can see the CO2 effect by itself is 1.6 over 1.6 watts per meter squared. You add any other greenhouse gases, you get up to about 2.5. You add in effects on stratospheric human activities affecting stratospheric ozone or affecting tropospheric ozone. Effects of stratospheric water vapor from methane in the stratosphere, which I won't go into. Changes in surface albedo due to land use changes. Effects of particle emissions, primarily a cooling effect from those. And here's the contrail effect by itself, singled out, and it's tiny. And here's the sun, changes in the solar flux over this time period. The net effect is something in the order of about 1.6 watts per meter squared. So we're comparing something that's in the order of 0.05 to 0.08 watts per meter squared to changes of 1.6 due to all human activities over this long time period. So aviation's a part of this is tiny. Now its current emissions are important, as I said, on the order of a couple percent from CO2 itself. If we actually go back here, the fact that the total is roughly double or triple, depending on whether you bring in that cirrus effect, or you can look here, relative to CO2, Europeans have put in, or talked about, I don't think they've actually instigated this yet, put in policies to control emissions based on a factor of 3 higher than the amount of CO2 emissions. And so implying that instead of 2.2 or 2%, more like 6 to 7% of the total world emissions in terms of then looking at controls. So there's been a lot of discussion going on in Europe about putting tight controls on aviation emissions. And the scientific community has been trying to fight that to some degree because, as I said, the lifetime of CO2 is so much longer than these other effects. And you really need to consider that if you're going to then look at what kind of policies you're developing. Accurate emission scenarios and understanding both the current emissions from aviation and future emissions is a tough job and remains an issue. There's new analysis coming out of FAA, Federal Aviation Administration, where they're trying to take into account very detailed analysis of each flight based on the actual flight recordings for a given year. That is likely to be the best analysis to date, but even so, there remains a lot of concerns. And in the projections, how will the future destinations for aviation change? We expect that more of the destinations are going to be in Asia and to the southern hemisphere than they have been in the past. And so the picture of emissions is likely to change, and what are likely to be, right now the flight corridors are dominated between what flights going on between the U.S. and Europe, but even that's begun to change as we've had more and more flights going to Asia. So that needs to be considered as we look at the projections. Switching to concerns about ozone. 90% of the ozone in the atmosphere is in the stratosphere, 10% in the troposphere. The emissions of nitrogen oxides from aviation can affect ozone in different ways. The process here shows how emissions in the lower atmosphere, this gray area, subsonic fleet is here, troposphere just above that, and roughly in the same altitude, and depending on latitude. And so the reaction of those nitrogen oxides with HO2 or with a hydrocarbon can produce the NO2. That NO2 can photolize, producing an oxygen atom plus the NO back again. And that oxygen atom, most likely, most of the time, will react with O2 in the presence of a third body. The third body is just N2, O2, or anything. It just works well in the presence of a third gas to produce ozone. And so one nitrogen oxide actually can produce a number of ozone molecules dependent on how much HOX, hydrogen oxides, or various hydrocarbons are around. Once you get above this region, the chemistry gets much simpler and ozone is destroyed by emissions. So if we were to look at supersonic aircraft, Mach greater than 1, shows the altitudes which the typical altitude at which aviation or aircraft would be flying, and for those kind of speeds, they would be flying at higher and higher altitudes depending on the Mach number, the amount that they're above the level of sound. And at those altitudes, you start really getting concerned about emissions of nitrogen oxide reacting directly with ozone, producing NO2. At those altitudes, the NO2, instead of photolizing, tends to react with an oxygen atom, forming the NO back. You've got a catalytic cycle for destroying ozones. Since that oxygen atom destroyed here normally would go to producing ozone, it's like destroying 2 ozones every time you go through this, and you can keep doing this many, many, many times just based on one emission of nitrogen oxide. Our focus here is on subsonic aircraft because the supersonic aircraft were not found to be economically efficient enough to be viable at this point yet. We've done a number of analyses of them over the years and worked with the airline companies to examine them, but right now it's kind of a dead issue. If things are typical, within the next decade it'll probably be raised again because somebody thinks they have a new way of developing the aircraft. And certainly it is desirable to go much faster between endpoints than current subsonic. But it also goes to cost more energy, so how can you do that efficiently is going to be another big concern. This is analysis that Ken Patton, Dr. Ken Patton, who works with me, actually did of the effects of aviation emissions on ozone. This is for the 2020 projections of aviation emissions. But basically, with altitude, so this is pressure level versus degrees latitude, for one of those emission scenarios like I showed you, and you get about a 5% increase in ozone in the upper troposphere. Not a huge change, but important enough change that that has a radiative influence in climate. If we were to contrast that type of change, though, relative to surface-related emissions, this was an analysis done by one of my students using the same model of the atmospheric chemistry. And it just shows January, 1 kilometer above the tropopause, 1 kilometer below the tropopause, and July, 1 kilometer above the tropopause and 1 kilometer below the tropopause. And basically, if you look in January, and the brown here is looking at mobile, so this is road traffic mostly, nitrogen oxides and hydrocarbon emissions and their effects on ozone in the upper troposphere and lower stratosphere is actually much more important than the emissions from aviation. In January, aviation only dominates when you get to high latitudes. So certainly the surface emissions we're putting into the atmosphere are having at least as important impact on the upper troposphere as the surface, as the emissions coming from aircraft. I mentioned the change in ozone has an effect on hydroxyl. This is the calculated change on hydroxyl. This is actually from the 1999 IPCC assessment because I didn't have time to ask Ken if he could give me a similar graph from our new analyses. But basically you get an increase in OH that results, I won't go through the chemistry, and that increase in OH decreases the amount of methane. That's why you get a cooling effect from the decrease in methane, from the change in methane, because methane is the OH increase decreases the amount of methane.
Let's just say increase in O3, not change.
I mean, increase ozone, I increase OH, but I decrease methane as a result, because OH plus methane is the primary sink, primary loss mechanism for removing methane from the atmosphere. So you have less methane and less of the radiative effect from methane on the atmosphere. Now, if we look at these kind of chemistry effects, where we're looking about nitrogen oxide emissions, we've learned a great deal since that IPCC 1999 assessment, but there's still a certain number of things we need to do. We need to do an analysis and compare models for a whole series of new calculations. My expectation is that the latest models is that we'll have much better agreement than we've had in the past in terms of what those effects are. But it just hasn't been done. There's been no new assessments, and new analyses need to be funded. Unfortunately, there's been no funding in the U.S. for looking at aviation effects on the atmosphere, in the global atmosphere, since about 2000, year 2000, when a big major NASA program ended, and FAA is trying to get some new funding going right now. We just put in a proposal a few weeks ago to try to get a little bit of funding, but it's at a very small level, and we really need to look at these issues more seriously than we currently are. Europeans have been putting more money into this by far than we have. Okay. Let's turn to contrails. Under the right conditions, and those right conditions being the right temperatures and being in a supersaturated region of the atmosphere, the water vapor emissions from aircraft can create contrails. Now, the basic physics of contrail formation is reasonably well understood, but some of the parameters at those specific altitudes still remain highly uncertain. We have a very limited data set to know how much of the air is actually supersaturated. Very new analysis. I was at Boeing last week giving a talk there, and they were telling me about new analysis they've been doing looking at the available Raywin sons from around the world, where you have to do a correction to get the upper troposphere right. And most people don't even realize they need to make a correction to the data sets to be able to look at the upper troposphere. But if you do that, you find that the supersaturated layers are actually very, very thin, on the order of a half a kilometer or less, implying if we could detect supersaturated layers, which would tend to under the right temperature conditions, lead to the formation of contrails, it wouldn't take a huge effort to either decrease in altitude or go slightly higher. to get out of the range of formation of contrails. But right now there's no such ability to do so because we just don't have the right data. So one of the issues still remaining, so we need understanding of those properties as a major issue. There's also issues with the plume itself and understanding exactly what's happening in this plume as you go over a few minutes and hours after the initial emission as to exactly what's happening within the plume in terms of physics and chemistry, and particularly what's happening to particles and particle formation and how that can then affect cirrus clouds. And I'll get more into that in a minute. So those contrails and those particles can affect cirrus, but those effects are extremely poorly understood and currently the subject of a lot of research, particularly in Europe. As I said, we don't have much funding for it over here. This is on persistent linear contrails. Most contrails only last a few minutes. Some contrails can last a few hours or more, and it is those contrails that are of concern to potentially leading to cirrus clouds. And contrails are basically ice, but they also have all these other emissions kind of trapped in there as well, these emissions of soot and sulfur, et cetera. And so there are some interesting things going on, but the primary thing is that it's ice. The geographic coverage of linear contrails depend on having the right conditions, supersaturation, the right temperature conditions, where the emissions are occurring, of course, the air traffic. And so we need to really know the relative humidity distribution in the atmosphere is a key part of this. That's the part that's not so well understood. And then the climate impact, we need to know the optical properties of those contrails, and some of that isn't real well understood either. Overall, the estimates of the effects of contrails have decreased by about half over the last, this is really going back to the 1999 assessment versus the 2005 fleet, which was really analyzed in 2007. So current emissions, current effects on contrails are estimated to be about half of what they were regionally thought to be. Still not negligible, but less concern. And perhaps avoidable if we can figure out how to do that. And we'll talk about trade-offs in a bit. Aviation impact cirrus is also extremely uncertain because we really don't understand the processes by which contrails and particles can influence cirrus. And as I said, there's a lot of uncertainties in that, and we still don't have a really good estimate of those effects. I realize time is passing quickly, so I'm going to try to finish. And so part of that is understanding, how well do we know the accumulation of the particle masses. Those particle masses are much smaller than from aviation than they occur from all other sources. Again, this is at altitude. This is 100 times the black carbon mass from aviation. It's about the same level as the amount from other sources from the Earth's surface. And so aviation is a relatively small player, but it's not necessarily negligible. A lot we need to understand about cirrus cloud formation and how these emissions can affect it, including the effects of long-lived contrails directly, aging contrails, and then also those particles. And I'm going to leave it there because it's highly uncertain. I mentioned the importance of metrics. Radiative forcing has long been the primary metric for studying aviation effects, but it's really not adequate. The reason is radiative forcing for some gases that are not well mixed, such as the changes in ozone, do not necessarily translate directly into the same temperature effects. And so you need a different multiplier. And so there's talks about putting a correction on those called EVAC that will make it more accurate. But even then, you would really, rather than radiative forcing, which is looking at the effect in, say, 1 year versus an atmosphere with no aviation, which is the kind of graphs I showed you before, we really would like to have an emissions-based metric. And there are various emissions-based metrics that have been developed. I was one of the leaders in developing a metric called global warming potentials. That is used in all, the Kyoto Agreement and all climate types of analyses. That does use radiative forcing within it, though. So one of my friends at Keith Shine from the UK developed an alternative concept where he basically uses an equation like I showed you earlier where you actually go to surface temperature. And so then you try to relate it to surface temperature. That has mixed effects. In the long run, that might be a better metric, but right now this is the one still GWPs is the one still heavily used. And the other approach is to use very simple models. And in fact, we're one of the people that have simple models that we also use. The international community is very concerned about trade-offs, and I'll just show you a few examples. Reduce cruise altitude because perhaps you want to reduce the amount of contrails. You don't know exactly where the supersaturated air is right now, and so you could say, oh, if I just fly lower, I won't have contrail formation, therefore I won't have that effect on climate. But you're going to increase the amount of fuel burn, and therefore the emissions of carbon dioxide. You need to take that into account. Increase the amount of emissions of nitrogen oxides, because you're not flying at the most efficient altitude for the airplane, and a corresponding effect on ozone. And so you need to consider all those things when you're trying to look at a trade-off like this. Operational changes to well, that's pretty much the same idea. Improve aerodynamic efficiency and reduce weight. Well, that will reduce the amount of CO2. It can also reduce the amount of noise and reduce the amount of NOx. So if done correctly, that's a win-win because it helps solve many, many different things. And you can look at many, many, many others. These are just a few examples. The FAA, I'm going to finish up with just a little talk about alternative fuels. The FAA currently is looking at what to do about future growth. How do you get aviation to play its part in the need to try to reduce the concerns about future climate? And even though the actual amount of aircraft are increasing. Carbon neutral growth relative to, say, 2008 emissions is the green line here. By making operational improvements, aviation can come closer to that green line. With improved aircraft technology, such as the kind of things Boeing's doing right now, you can further come closer to that line. And what the FAA is currently looking at is alternative fuels towards actually getting to the green line. Those fuels can reduce the emissions that impact global climate change and air quality, thus improving the environment. However, they do expand, and they also expand and diversify energy supplies beyond conventional petroleum, so that can help with price concerns for future years. They need to be produced in large quantities, though, without adverse impact on our land and water resources. And this is where a lot of analysis is going in right now towards how we're going to get there. And the fuel needs to be compatible with the existing infrastructure. You know, we're going to build a whole new set of aviation to deal with these. Several different options that are being considered is to look at continuing use of petroleum, but try to develop ultra-low sulfur jet fuel. Tell you the truth, I'm not sure that one's worth it. You end up with the increased greenhouse gas effect from the extra energy you put into producing the low sulfur fuel in the first place. But you do reduce the impact on air quality because you're not putting sulfur dioxides into the atmosphere. The better approach seems to be to develop synthetic fuel, jet fuel. That is functionally similar to Jet A used now. It has very low to zero amounts of aromatic compounds, much less likelihood of formation of particles than you had before, and no sulfur, so no sulfur particles. It can be created from a variety of different feedstocks, and I'll talk about those just very, very quickly. The problem is we need to be able to go from something like this for soil oil, which they think would need a huge amount of the U.S. agricultural production to be able to make it for our own needs, down to something like this yellow thing, which is a feedstock that is still uncertain. The closest we're coming to that is some analyses of using algae as the feedstock. And there's a variety of analysis going on looking at that. So I'm going to end there. Thank you, and I'll open it up for questions.
Yeah, when you hear these things like, you don't drive your car much, and then you take a flight to the West Coast and back, and you've driven 20,000 miles and everything. So that's complete nonsense based upon.
If you don't count the fact that you're sharing it with 160 other passengers.
No. But I mean, if you try to contribute your additional, that's just based on the CO2, right?
Yeah, it's really just based on CO2.
So, but the CO2 from the plane and other stuff is much more complex than just coming it out of the tailpipe of the car. I mean, isn't that sort of...
Right, but it's the same CO2, and CO2 coming out of the car is going to have the same atmospheric lifetime. So trying to do that carbon equivalent, or trying to do carbon, doing your carbon footprint for that, and then perhaps paying somebody to plant that number of trees or something, it is not a bad way of looking at it. It's just a very simplified way of looking at it. Yes.
My question is alternative fuels. Let's consider if they switch to biomass fuel. So, assuming that biomass is...
And actually, there are some plants they are considering they think they can produce efficiently enough. I couldn't tell you what those were, so I kind of left that out of my talk.
Assuming the biomass, then that takes care of the CO2 problem. But, from your presentation, it seems to me that NOx is a major issue. And of course, most of that NOx is not really fuel NOx, it's air NOx, because it's dirty. So the question is that if you switch to some of these carbon neutral fuel, does that really going to impact the climate change as you explained nicely from the aviation, or that's only a small portion of it? Or how does that
The primary effect would be on some parts of it, much less particles and the decreased CO2, because the CO2 is coming back out of the biosphere. But well, still you're still, even at its worst, you're multiplying that by a factor of 3. So, and you get rid of the particles, you're getting rid of some other fraction of it. So you are helping it, but you are going to produce the nitrogen oxides. But the question is, can we through new engine technology, through trade-offs for lean versus, so developing low NOx burners, and there have been a number of approaches developed for doing that, some better than others, usually with a cost in terms of how much fuel you're burning. But you could force the switch then to low NOx engines. Starts really having a huge impact. You still got the problem with contrails, but what people are trying to do there is looking at how can we be smarter? How can we detect that we'll be in a situation where we would form a contrail and just try to avoid it? A lot of work to be done yet, but that's the kind of thing that people are looking at.
What is a cloud albedo? We had that in 1750 scenario, and then that had a big negative effect on warming.
It's a cloud albedo. I think the effect there was the effects of particles on cloud albedo, on the reflectivity of clouds, and therefore leading to a cooling effect, making clouds look darker.
And so is that a viable approach?
Or brighter, actually.
Is
Sorry.
that an approach that might be considered as a way to cool? I mean, if it has a...
Well, no, we don't want to go there. We're doing other pollution to... I don't like the ideas of adding extra pollutants to be able to... You're solving one problem, you're going to create other problems.
So, but you said it was to increase the reflectivity?
And that's low-level clouds, by the way, because those are based off of surface emissions, not off of the aviation.
So the cirrus clouds increase in those Increasing CO2 clouds increases warming
Right.
because it's more like a blanket.
That's right.
But clouds also reflect, so it's the low level.
You have to
reflect?
primarily. When you look at cirrus, you have to do both, but the primary effect is warming as you increase the amount of cirrus.
Lower level clouds.
Lower level clouds can go either direction depending on what you're doing to them in terms of making them brighter or darker and what type of clouds are formed. And that's all part of the climate system modeling that we do. Yeah.
So what was the cloud albedo in 1750? What was contributing to that? And why that wasn't something natural at the time?
This is the change since 1750. So clouds then would have had very little influence from human activities. And so this is saying, well, how, particularly because of our emissions of sulfur, our emissions of soot, our emissions of other particles into the atmosphere that can act as cloud condensation nuclei, you change the amount of cloudiness, you change the type of clouds, you change the darkness and brightness of clouds, and those can have an influence on climate.
Has the overall atmospheric water vapor during the measured time period, has it remained fairly stagnant, or has water vapor increased as well in the atmosphere?
Actually, as the atmosphere is warmed, we know that the amount of water vapor in the atmosphere has increased, as we would expect it to. The atmosphere can hold more water vapor as it warms. So, and we have measurements of satellites to show that.
It's the result of global warming as opposed to contributed to global warming. Well,
it's a feedback. So yeah, water vapor. There's feedbacks. Human activities themselves have very little influence on the water vapor in the atmosphere, but water vapor is a very key part. Water in general is a key part of the climate system. So as the atmosphere warms, the atmosphere can hold more water vapor. That water vapor further adds to the warming. That is all taken into account in the analysis.
And does that include the trillions of water that gets evaporated from cooling towers?
Yes, but that's still tiny compared to the amount of evaporation that goes on naturally. Yeah, that is considered. People have done those analyses. Yeah.
What's the status of the ozone layer? Has the banning of the fluorohydrocarbons,
You didn't see Science from 2 weeks ago, or last week, whenever. I had an article in Science last week, October 2nd issue, which I think kind of got to everybody's doors last week. The general thoughts have been that because of the Montreal Protocol and the fact we effectively have eliminated emissions of, or very soon we'll have eliminated emissions of chlorine and bromine gases. We've already eliminated a number of them, but not all. That the atmosphere will recover globally roughly by 2050, and the Antarctic ozone hole a little later, more like 2065. However, a paper that I had in Science, along with another paper by Ravi Shankar and colleagues from NOAA in Boulder, basically talks about how increases in, they talked only about nitrous oxide increasing. If you talked about the greenhouse gases that are changing the most, it's CO2, methane, then nitrous oxide, then the chlorofluorocarbons actually, which were also greenhouse gases, and then a number of other gases, but very, very minor effects from those. Well, N2O is the third most changing greenhouse gas. N2O is also the primary source of nitrogen oxides in the stratosphere. We've known that since 30 years ago. That's why Paul Crutzen got the Nobel Prize in 1996, was for discovering that. But people seem to have forgotten about the fact that N2O is increasing and could influence future levels of ozone and may prevent us from actually having a recovery of ozone. So that's what my article is about, and that's what the Ravi Shankar's paper is about. In addition, in my article, I also talk about methane increasing and the fact that methane affects the amount of hydrogen oxides in the stratosphere, and that also will have an influence on ozone and also needs to be considered as we look at future levels of ozone. We just started a new international ozone assessment. I've been involved in these since the first one was done in 1990. Actually, it was before that. Late 1980s, I guess we did one. And no, it actually started in 1980. It goes back further than I thought. So the first international ozone assessment was done around 1980. And I've been a lead author on pretty much every one since. And we just started this new assessment, and I'm working on the chapter relating to policy questions related to ozone. And we found out the last few years that the usual analysis approach that's been used is only concentrated on chlorine and bromine gases, just is not sufficient. So we're actually going back to using full models of the atmosphere to try to do a new analysis where we can take into account these N2O and methane effects that haven't been considered in previous policy considerations. Yeah.
Thinking about the public policy issues of air transport versus land transport and where that fits in the mixture. I'll give you a very specific question. A month from today, the university will move the football team to Minneapolis for the weekend. You charter air 500 miles for 100 people versus bus. What's the difference between moving 100 people 500 miles on the highway contrasted with airline? And should that be in the public policy?
Well, they all taking their own car, or
let's assume bus. Let's
assume they all doing the same.
Trip,
yeah, same vehicle. I think if it was the same vehicle, there'd be no question the bus would be a whole lot more efficient, but take a lot longer.
What I'm really asking is, should promoting land transport versus airline?
If we had rapid rail between here and Minneapolis, I'd say there'd be no question that would be the way to do it, because you not only would get there roughly the same time by the time you take into account getting in the airplane and back off the airplane and getting your bags, but you would also be using a whole lot less energy. And this is one of the reasons for trying to develop rapid transit, fast rail within the Midwest. I'm going to end there, and I'll be happy to answer questions individually, but thank you all.